introduction. I'll be talking about aligning AI with human norms, multi-objective deep reinforcement learning with active preference solicitation. As Luciana said, this was done as part of my master's research. It has nothing to do with my current job, but I'm still very enthusiastic about this topic and hope to spread the message that I came up with, essentially. So I'll start with a small motivation, namely, my research is about deep reinforcement learning, and I like to call it a powerful optimization framework for finding optimal behaviors in some sort of sequential decision-making tasks, which can be quite broadly defined. And this framework and all the advances in deep learning, as you're probably familiar with, have led to a bunch of quite impressive results. And one of them being the DeepMind AlphaGo system, which 5 years ago actually beat the world champion in this very complex game of Go. And slowly but surely, we're starting to see more real-world applications or applications that have more impact to the real world than playing games. And a very prominent one is, of course, with a big economic interest, is this chip design problem. So we can train reinforcement learning agents to come up with computer chips much better and faster than experts. But this is just a small list of examples. On the right-hand side, you can see many more which we can expect to see in the future, such as robot locomotion, automated factories, power grid optimization, and self-driving cars. We can expect many of these things being powered by some sort of reinforcement learning, perhaps, if the progress continues the way it is right now. And this is all great, but also a little bit scary. And before I tell you why I think this progress might be scary in some sense, I want to revise the reinforcement learning framework that we build our research on right now. So reinforcement learning, it typically models some intelligent agent acting in a Markov decision process, MDP. There are many extensions to this framework, of course, but I'm just presenting the most simple one. And this process, it is a mathematical structure. It consists of a set of states that the agent can be in, a set of actions that it can do, transition probabilities, which determine what the next thing will be that happens, a reward function, and the starting state distribution. And the way it works, the way we model this process, is we have an agent which takes an action at each time step according to some policy pi. Pi, it determines how this agent behaves, and it takes a state and gives a distribution over actions. And then once the agent takes this action, it gives it to the environment, and the environment gives back a next state and a reward that the agent can then use to learn. And typically our goal is in reinforcement learning, our goal typically is to find this policy pi, which maximizes cumulative rewards in expectation. So we want to maximize some sort of sum of rewards that we get in the future, which might be, of course, discounted by some factor gamma that just determines how far we actually want to look into the future. But for now, you can assume that this is just set to 1. So this is the basic framework, and what my research deals with is this reward function. So why is this reward function a problem in some sense? Well, here's a funny example by OpenAI, where they trained a team. So this is, in fact, more than one agent. This is 2 teams of 2 agents of hide and seek agents. So they wanted to learn this game of hide and seek with some objects in the physics simulation. And the red team gets a very simple reward of +1 if it sees the blue team, and the blue team gets a reward of -1 if it is seen, and also reward of +1 if it hides from the red team at each time step, I believe. And what they found out, besides the agents actually being quite impressive at solving this task, sometimes they would come up with quite absurd strategies. Where absurd meaning that they actually break the physics engine. And on the left-hand side, you can see, for example, the red team agent managing to bump this ramp into the wall in a way such that it gains a lot of upwards momentum, which is, of course, not intended by the designers of this simulation. And on the right-hand side, you can actually see a counter strategy to this, where the agent manages to get this ramp out of bounds. So this is a funny example, and sort of shows that in some sense, these deep RL agents can come up with ways to exploit the reward function. But you could think maybe this is just an edge case, and this just happens in some games because we didn't pay enough attention to the reward and not enough attention to the simulation. But in fact, this is actually a very common thing in reinforcement learning. So there's a very cool list by Victoria Krakovna, which I believe is a researcher at DeepMind. And I shared this in the slides, which you can, I highly encourage you to check out. It's very funny also. And yeah, the message here is that if we look at all these types of problems that we have been studying in reinforcement learning, actually this problem of not paying enough attention to the reward function happens all the time, in essence. Yeah, this is a big problem, because if we expect, as I said before, reinforcement learning agents to act in the real world to optimize some sort of procedure, sometimes with a lot of economic incentives in mind, of course, as well, then we might expect the agents to mess up certain things without human values in mind, for example. So this has led to a broad discussion in the past years, and actually to a much, well, it is part of a much larger research agenda, I think, of value alignment, which I think this community here is very well familiar with. And the problem of value alignment, of course, goes much beyond reinforcement learning and reward function design, but also incorporates ethics and governance. But in fact, this is very important, because we cannot solve this reward function problem, I believe, by itself from this technical aspect. But we also have to keep in mind that there is always this normative question of what values should an AI follow to begin with. It's not only hard to find the reward function such that the agent does exactly what we specified it to do. It's also hard to even come up with something to specify in the first place, because sometimes there might be some conflict between what the agent should really do. And not even humans have a very clear thing in mind to do. So this technical question, this first one, has been tackled by reinforcement learning research quite a bit in the past, where they studied basically, okay, we have some sort of reward in mind that we want the agent to follow, but it's hard to specify. So what do we do instead? Well, we can try to learn this reward function from some sort of human inputs. And many prominent human inputs, or many popular ones, are natural language demonstrations, pairwise preferences, human intervention. There are many more types of feedback you can imagine for these agents to act upon. But yeah, essentially the problem here is that these approaches, they only learn from one expert most of the time. So there is no way of keeping this normative question in mind of what values should the AI follow to begin with. What do we do if we cannot even incorporate from one expert these demonstrations into the system? Because then the agent will just learn from one person, but this person's views might not reflect humanity's views. So what we study in this work is essentially how to keep the second question in mind. We of course cannot solve it, since this is a philosophical question, and I don't think this is easy to solve. But the main goal here is to look at scenarios like this, where we have multiple experts that come up with different preferences in mind, and we still want the agent to do something useful in the world, and there will always be certain behaviors that are dominating others. So there will be behaviors that a lot of experts agree upon, which are good, and a lot of behaviors which are bad. And we want to find these policies, essentially, that most experts agree on, and then leave some room for fine-tuning the agents with respect to specific details. So this is what we do. We study how to learn reward functions that can trade off different objectives. Then we propose an algorithm, essentially, which is called multi-objective reinforced active learning, which I'll call MORAL from now on. And it combines learning from demonstrations and pairwise preferences. And finally, we demonstrate the effectiveness of MORAL in the context of learning norms. If there are any questions here, please interrupt me. But I think I'll leave probably a lot of time at the end still to answer questions. So in case there are no very pressing questions, I'll move on here.
Yeah, if someone wants, you can also post the questions in the chat, then we can pick it up then later. So okay. But first question? No. Okay, Markus, I think you can continue.
Perfect. Yeah, this was just the motivation. So I was hoping no questions to arise here. So that's good. So now comes the technical part of the talk, I would say, which is this algorithm that we came up with. And it consists of two steps, essentially. So the first step is learning from demonstrations, and the second step is kind of combining different demonstrations into one final policy. And both of these steps, they combine sort of state-of-the-art approaches for their respective fields, namely this learning from demonstrations and learning from preferences. But we adapt them in a way to work together. And you'll see in the examples later why we chose this essentially. So I'll skip the first step, not completely, but just briefly, because it's a bit technical and I don't think there is much interesting to see there. But in a nutshell, step one, it learns from a bunch of different experts different reward functions. So assuming we can learn a reward function from a single expert, we can repeat that, and then we end up with multiple reward functions, and that's essentially a vector of reward functions that we then have, which represent what different experts deem good and bad in the world. So this is the first step, and I'll just briefly mention how this is done. Since we're doing deep learning and we don't really have access to features of the world, we have to do everything in some sort of end-to-end fashion with learning everything from scratch. But there's actually a very, very cool framework which is called adversarial inverse reinforcement learning. So inverse reinforcement learning, it's, by the way, in case you're not familiar with it, it's how we extract reward functions from demonstrations usually. And what this does is it takes a set of demonstrations so this just shows the single expert case. It takes demonstrations from a single expert, multiple ones, and then it trains sort of a generative adversarial network. So it trains a policy pi, which tries to imitate these demonstrations. And at the same time, it trains a neural network which discriminates behavior from this agent and the real demonstrations. So all the time, the agent tries to do something that closely resembles these demonstrations, while the discriminator tries to get some clips from the agent and some clips from the actual expert and tries to say, okay, this came from the agent, this came from the demonstration data set. And the reason why we do this is because you can actually mathematically show that under some certain assumptions, we then end up with a reward function that we can extract from the discriminator, which will yield rewards in such a way that if we optimize for this reward function, we end up with behavior that looks like the experts. So it's a reward function that imitates the expert demonstrations in some sense. So this is quite convenient, and we can repeat this for multiple experts and end up with this reward function R. But in our case, actually, we can also incorporate another primary reward function RP. And this is totally optional, but you could think of maybe some designer designing some reinforcement learning system and having some primary reward in mind. This will be more clear at the experiments I'll present later. So the reason why we include more than just these learned reward functions is just that this allows for more flexibility. And then the problem is, of course, we have now these representations of what different experts like and do not like, but how do we combine this into a final reward? The agent needs to do something at the end of the day. So we need to find a way to fine-tune this to different preferences. So the idea here is that we can just linearly scalarize this reward. So we multiply this reward function with a vector W. And since we do not know how to combine these f theta are not really interpretable, since these are all neural network outputs. We learn these combinations of reward functions from preferences, and this is what we do in step 2. And I guess this is more the interesting part, so I'll put a bit more effort into explaining this step number 2. So now we've learned a representation of different experts, and we would like to come up with an algorithm that can in real time sort of tune this expert to optimize either a certain combination of these experts' desires. And of course, it's really important to learn this correctly, because sometimes one expert might say, I like A and do not like B, and another expert says exactly the opposite. So if we were just taking the mean over these two reward functions, then the agent would not know what to do at all. So we need to learn this in some reasonable way. We can't just take the mean and hope that it satisfies all people's preferences. So what we do here is, in the second step, we do active learning, active moral, what we call it. And it consists of 3 steps, essentially. In the first step, we optimize for some fixed reward function with proximal policy optimization. This is a state-of-the-art reinforcement learning algorithm. I won't go into detail. It's a black box that optimizes this reward function. And the reward function we choose is the posterior mean of this W transposed R, where we have we are maintaining a distribution over these W's. So we want to not only learn a W, we actually learn a distribution, which also gives us some uncertainty estimates. And in this optimization step, we just give the agent our best guess of what the combination should be right now and optimize for that for a little bit. Then the agent acts in the world, tries to satisfy this combination of rewards. And then after some time, we give another expert a query, which consists of 2 clips of the agent's experience. And then the expert here can decide which of these 2 clips it deems more preferable. And then we use this answer from the expert to update our combination of reward functions by using Bayesian learning, essentially. And the way this is done is we of course have to define some sort of mathematical model, and this is a bit more involved, but I hope it won't get too complicated. So there's actually quite a lot of research on pairwise preference learning in this sequential decision-making context, and it turns out you can actually adapt this to a multi-objective setting, where you say that our model of the expert preference, the expert's preferences here, are given by this following equation. So this is a Bradley-Terry model, where we value clips or trajectories that achieve a higher scalarized reward, exponentially higher, in proportion to this reward function here. So that's the equation. And by the way, R of tau, some trajectory, it just denotes the rewards we get throughout this clip, this period of time. This is our model of pairwise preferences. And then we can use this model, this likelihood, to update in a Bayesian manner, where we just say that the posterior of this weight W, given some answers by the expert, is just proportional to some prior, which we have to specify. And then we multiply it with the likelihoods that we obtain through time. And then hopefully we obtain, over time, the agent acts, and over time we can fine-tune the agent to specific different values, you could say. And in our experiments, we always use a prior that's uniform over all positive weights. So we start out agnostic totally with respect to all the expert reward functions. This can be, of course, changed, but in our case, this was the easiest to come up with experiments, essentially. And there's one technical detail, though. This Bayesian learning, we, of course, do not have an exact representation of, like, an analytical expression of this posterior, so we need to employ some methods to sample weights that we deem likely, and we use our Markov chain Monte Carlo for this. But this is just a technical detail. So this is how we update. Given an answer, a pairwise preference from the expert, we can then use this to update. But I haven't told you how we choose the query. And this is actually a very crucial step, because the way reinforcement learning agents work is that they learn through a lot of trial and error. So they will just run around in the world and try to maximize the reward in some absurd way. And of course, if we do not pay any attention how to query an expert, then if we just randomly sample from the agent's experience, we will just sample a lot of boring behaviors, you could say. So, for example, most of the time, the agent will just start out by running against the wall, and this will be most of its time being spent, essentially. So if we just randomly sample from all of this experience, we'll probably sample 2 clips where the agent does absolutely nothing or runs against the wall, and then there's not really anything to compare. So we want to extract sort of these interesting cases where the agent runs into some value conflict, and this is the equation that essentially gives us these clips where we expect to learn most from. So we want to maximize over all pairs of trajectories or clips some sort of lower bound, and this lower bound, essentially each of these terms in here, they give us the volume that we can remove from this posterior distribution if the expert answers in a certain way, and we take a minimum over both of the possible answers that the expert can give. So no matter what answer the expert gives, we want to maximize the amount of volume we remove from the posterior distribution, which in other terms, in non-mathematical terms, just means the amount of information we expect to get out of this answer. So this is what we optimize for. And this, of course, we cannot really solve. It's kind of intractable in the real world. So what we do is, since reinforcement learning, as I just said, it takes a lot of time to optimize for its rewards, we just sample from the agent's experience and then look at this metric. This is essentially just a number for each pair of trajectories. And then we keep track of the best clip, the best experience the agent has experienced so far, and use that after some fixed amount of time to update our preferences, or to query the expert, sorry. And then this leads us to the following algorithm. So we start out with some demonstrations by the experts. Then we learn a representation of these expert preferences, essentially, in a vector valued reward function. And in the second step, we learn how the agent, or we provide essentially a way to fine-tune the agent with respect to certain combinations of these reward functions to come up with a final behavior. All right, so now I'll talk about results. And this is one caveat of the research, I suppose, is that we evaluate our research only in grid worlds, which are discrete environments where the agent finds itself in the two-dimensional grid, and it can move in one of the four directions, and then do, in our case, also something else, namely interact with its neighboring cells or do nothing. And the reason why we evaluate here is because this allows, of course, for very easy experimental workflow, and we can easily iterate on the environment and automatically conduct these studies. And also one reason is that these inverse reinforcement learning techniques, they are very hard to train, and most of the value alignment research in this field is done in grid worlds, unfortunately. So this is one big next research step, I would say. But nonetheless, these experiments can provide valuable insight, which is why we rely on them. And yeah, we present two environments. One is really simple. One is called burning warehouse, where the agent finds itself in a burning warehouse, and its primary goal is actually to extinguish fire, or to walk to a fire extinguisher and then use it. But also we assume that there are a lot of workers which are lost in this warehouse, and they do not know how to escape the building. So we would like, in this case, we would like the agent to not only follow this primary goal and not only optimize that, because we assume that if it walks past a person that is lost, or if a human were to walk past a person that is lost, it would probably help him and help them and tell them, look, here's the way out. So this is kind of what we want to achieve here. And in delivery, we have actually much more conflict between different values. So here we have many more things to do, and also a primary goal of delivering packages. So this is sort of an agent walking on a street, and then we assume that it could encounter some people that are in need of help. Maybe they tripped or they lost their phone. It also could clean up the street in case it's not too much effort. And there are also vases that it should avoid, because we do not want to break vases for no reason. So these are the two environments that we study. And I'll start with the results in the first environment. So in the first environment, we train the agent in the following way. So we provide in the first step just demonstrations from a single expert, and we assume that this single expert, it really wants to save these people that are lost. So these demonstrations, they just go go up to the people, tell them, look, or interact with the cell, essentially, meaning telling them how to get out. And then we train for this in the first step, and we can see that the inverse reinforcement learning works. So we do learn a policy that imitates this behavior of saving all the people in a reasonable time frame. But now we, of course, have this conflict between this primary goal and this demonstrated norm, you could say, which we want to incorporate, and this is where the second step comes in. And here we also chose to give preferences in a very principled way. In the second environment, this will be a bit different, but here we assumed that there is only one reasonable behavior, which is save all the people and then go and extinguish as much fire as you can. And this is the preferences we provide. So given two trajectories, we always prefer the trajectory where more people are saved. And if both of the trajectories save the same amount of people, we prefer the one which extinguishes more fire. And we can see the results on the left-hand side. So here we plot for each point during the second step the objectives that the agent achieves, and it starts out here doing nothing, just wandering around, being confused. And then after a few time steps, it receives these preferences. And of course, at the start, it doesn't save any people, so it receives preferences of please save more people, and it learns this. And once it has learned a policy that saves people all the time, it then understands that we give it more preferences, which also take into account this primary goal, and then it converges to a solution that does kind of both as much as possible. And we compare this to just manually choosing these combination weights in the second step. And we can see, so these are these colored dots. And we can see that we actually find a solution which we, first of all, wouldn't have found by just doing a grid search with weights in 0.05 steps. So we find a policy that we wouldn't have found, but we actually directly obtain something that resembles our preferences without having to search forever for some linear combination of reward functions. So this is good news, I guess. And on the right-hand side, you can see that this is actually quite rather, well, these are all relative terms, but this is rather sample efficient. So we use here on the left-hand side 25 queries in total, and you can see that this does suffice to converge to a policy that does the best of both worlds. So at the end, I'll just present one more example, namely this delivery environment, because the last one was very simple. And here is I guess the most interesting, here are the most interesting results. So what we do here is that we give the agent the primary reward of +1. This was this RP in our vector value reward. And then we assume that we have two experts, which both like something, which both think that the agent should do something a little bit different. And one expert thinks that if the agent encounters a person, it should always help them. And the other expert thinks, well, please, this street is so dirty. I think the agent should put more effort into cleaning the streets if it walks past the dirty tiles. Both of them, however, agree that the vases should not be broken. So this is sort of the agreement point between the two. And then we give these we give our algorithm demonstrations from these two different experts, which have, of course, some conflict in them. And in the second step, we try to combine these into one final policy, or we try to study, can we now come up with policies that, first of all, not only imitate each of these experts, but also kind of get the best of both worlds. And maybe you walk past the person, but right next to you, there is also some trash that you could pick up. So why not do both if you have time for it? Of course, this depends on how much you value which of the experts' preferences. And this is what we study here. So we do actually a simulation study where we provide the agent with a bunch of different preferences, and we do it in an automated way. So our preferences are represented by a vector. And the way we give answers to these pairwise queries in the second step is that we look at two clips as before, where the clips are represented by the numbers of objectives. So for example, the agent might just deliver one package, help 3 people, and clean 2 tiles. The vase here is omitted for simplicity. And in the second clip, the agent delivers packages, but doesn't really care about helping people or cleaning tiles. And then, for instance, we define a preference vector M, which defines a ratio 2 to 3 to 2 between these 3 objectives. And we would like to choose the clip that more closely represents this ratio. So what we do is we take the clip that has a lower Kullback-Leibler divergence, which is just a way of measuring distances between distributions. In our case, this is just a discrete distribution. So here the S1 would win because 1, 3, 2 is quite close in ratios to a 2 to 3 to 2 ratio. And if we do that for a bunch of different vectors M, so now we just want to see, can we fine-tune the agents to all of these different preferences? Then we do see that we get a wide variety of behaviors, which is good. So this means that we can actually fine-tune the agent. And also what we see is that the policies that we achieve very closely resemble what we gave during these preferences stages. So we don't only get a lot of random behavior. For each of these behavior points, these actually represent what we were aiming for while training. So what we plot here is sort of a two-dimensional projection of these three first objectives, since three-dimensional plotting is not really beautiful. And the colors in the first row represent always the third objective, and in the second row they represent how far the achieved objectives are away from the preferences that we gave during training. So what we can see from the first row essentially is that we do achieve, I mean, you would need some time to look at this in more detail, but essentially we can read from this that we can get policies that do quite well in certain regards. So let's say, for example, we take this point here. It manages to clean a lot of tiles, also deliver a lot of packages, and still help some people, while not breaking a lot of vases, which are these gray circles around. So we can get a good trade-off between all of different objectives. But also we can choose to do something else and maybe help more people at the cost of cleaning less and delivering fewer packages. The more interesting point, though, is this lower row where we see that for most of these points, these colors are very dark, indicating that, yeah, for example, here we perhaps provided a ratio of 3 to 7 to 5 or something, for example. Then this just means that, yeah, the ratio was actually attained, and the agent didn't just come up with some other behavior that it deemed interesting. So this is sort of this alignment that we are trying to measure with the preferences during training. All right, then one more baseline I wanted to mention here is that, of course, our method, it involves a lot of different algorithms, or it combines a lot of different methods. And you could maybe say that this is a little bit too complicated and too convoluted. Why do we not just skip some of these steps? And one of the main criticisms, I guess, you could come up with is, why do we need this first step of learning reward functions from different experts if at the end of the day there's just one expert that determines how we fine-tune and what behavior we achieve at the end of the day? So this is a very valid criticism, and this is kind of what we test here. What happens if we skip this first step and only train an agent end-to-end using preferences? And this is essentially this was already there, this algorithm. It's called deep reinforcement learning from human preferences, which employs a similar model, but now it learns only from preferences using this Bradley-Terry model, and it doesn't use any Bayesian updating. It just uses backpropagation or gradient descent. And what we found is that, of course, there are some fundamental differences, namely that this approach here, it does not allow for any primary reward or any combination of rewards, and it also doesn't allow for any demonstrations, or not easily at least, to be incorporated. So what we do to make it a bit more of a fair comparison, we just provide many more preferences to this approach. So we here have 1,000 preferences, for example, in the burning warehouse environment, and see if we can at least get some sort of similar behavior out. But what we found is that actually, if we just train from preferences end to end, besides taking a lot more time, is that we actually do not converge to a solution that is Pareto efficient. So here you can see that DRLHP, it manages, so we give preferences in the same way as before, by the way. So here we see that it manages to understand that we care about saving people, but it does not understand that we also care about extinguishing fire, or it does not understand it enough, at least. So it really lags behind in this primary goal, whereas moral just outperforms it here and just finds an essentially much better solution in all regards, at least in this environment. And we also repeat the experiment for a bunch of different preferences in the bigger environment. And we sort of see a similar trend. Interestingly, though, we see also that DRLHP, it really has troubles finding out these different nuances between experts' preferences. So in all of these cases, this orange curve DRLHP, it sort of converges to it does understand some sort of preferences that we provide, but in most cases the differences are much more subtle. So it's sort of always a mean solution, and it cannot pick up that we might care about not destroying this vase in the corner, or it might care about we might care about really helping this person that we just ran past. It sort of washes over everything because it's an end-to-end deep learning system. Whereas moral, it manages to give us a much more fine-grained control over which things to prioritize and which not. So at last, I think I'm already taking a lot of time, but this is the last slide, the second last slide. So this is just an ablation study, essentially, and also a robustness study where, since everything we do is automated, first of all, we would like to see how efficient this is. And we can see that by using this active querying procedure, we actually are much more efficient and actually much more close to the expert's preferences than what we would attain by just randomly querying. But this is kind of as expected, as I said before. And the right-hand side is much more important, which is we test what happens if the expert has a lot of noise in its decision-making process in the second step. So what if the expert sometimes gives a very contradictory evidence? And we model this by adding some random noise with some probability, then the expert gives a random answer. And we do see that, of course, the error, so this is how far the policy that we obtain is from the preferences that we give it during training. We do see that it increases, but still it is still up to a noise of 0.3, which is already like each third answer is completely arbitrary. It's still better or as good as the random queries. So that is sort of a sanity check of this approach. So in conclusion, we propose moral. It's a method for combining multiple sources of rewards, and be sure that through multi-objective optimization, we can actually recover a wide variety of trade-offs and actually generalize a little bit from this demonstrated behavior. We don't just have to imitate it, we can actually combine the best of different worlds. And we compare this to a baseline approach, this DRLHP, and we found that previous methods, they really lack the ability to deal with conflicting objectives. And we also find that actively learning a distribution over these combination weights is quite effective for learning efficient policies. All right, that is it from my side. Thank you very much.
Nice. So yeah, big round of virtual applauses or oh, such a Markus. Yeah, thank you very much. Yeah, do we have questions? You can either raise your hand or just pick up. Yeah, yeah, I see one. So yeah, go ahead.
Hi, Markus. Thank you for the presentation. I think it's a really interesting approach. So my question might be something that you already showed, but I lost the internet for a while. It was basically that how many human preference, so how many trainers do you need? Or have you done any experiments on at what point does providing the number of trainers just plateau what the model can learn from, different people? So where I come from is from the field of medical image segmentation, where contrast in medical images is not so good. So you get multiple doctors to annotate, any kind of organs inside your body. Then the question arises, how many people do we actually need to annotate those things? Because at some point you will have diminishing returns.
Okay. Well, I think maybe it's a little bit of a different view, because in our case, I'm not sure if I understood the question correctly, but in our case, it's like the more experts we have, we assume that there is more disagreement, I guess. And in your case, probably you're hoping to get more agreement between doctors. Is that right? Or more information?
It's quite possible that the annotation styles of two doctors in our cohort might be same. Yeah.
Okay. Well, we didn't check how far we can push the amount of experts. The nice thing about this approach is that since in the second step we just employ Bayesian learning, we can just it scales. So definitely we can just scale it up and see what happens. But we didn't test it. It's a bit hard in these environments because we would have to come up with environments where a lot more disagreement is possible. But if, of course, we kept the environment to this simple setting, and then there's a lot of overlap between some experts, then these weights, they'll just learn that. So this will not pose any problem, I think. As long as there's overlap. The more disagreement we have, the more harder it will get, of course, to fine tune to a specific preference. Yeah. I hope that answers your question in some form.
Yeah. Yes.
Okay, great. Thank you. Thank you very much for the question. Yeah. Someone else has some questions for Markus.
Yeah, I have a question.
Go ahead.
So Markus, thanks a lot for the great talk. Really insightful, well presented. And I had a question about how you see this relating to meaningful human control. And so I guess one of the questions I had, and then I'll let you comment and answer on my question, is, so now you've captured, you know, kind of a reasonable quantification of combining multiple sources of rewards, perhaps equally well as humans would be able, human experts would be able to do it. So we can argue about that. But the question is now, how would that work? And would you be able to, as an expert, kind of question, you know, the policies and that actually roll out of your approach? Would you be able to say, well, no, it's here where it's going wrong, or so could you comment on that?
Yes. So of course, I think this approach has advantages and disadvantages. I think one of the disadvantages is, of course, if you were to really track back who is responsible for the actions of the agents, is a bit hard here, because we have these multiple steps where demonstrations are involved, and also then a trade-off is involved by Paris preferences. However, that does not mean that we're completely lost. So we, of course, can inspect the demonstrations of the experts in the first step and see if there was actually really a malicious behavior in there, for example, in the worst case. If this is not the case, then we can assume that this is, of course, not at least the experts' faults in the first step. In the second step, yeah, I mean, what we show essentially here is that the preferences that we give are closely imitated or closely learned by the agent. So this only gives us some sort of guarantee that the agent will not do something completely different, but it, of course, doesn't shield us from adversarial attacks or something else, and we will not be able to tell, like, depending on the case, who essentially was responsible for what happens. Yeah.
If I may pitch in also.
Great answer.
Yeah.
So we're still in business.
Yeah.
Okay.
Yes.
If I may pitch in also, I really like about Markus' approach there. And the moral is because when you divide, you have the second step. The person that gives this preference could change according to situations, according to context. So that will also track the reasons of a specific person. Say robots delivering close to your home, it can kind of tailor this according to some kind of agreed upon rewards, can try to tailor this to your preferences there, but also when it goes to another neighborhood, can also tailor to another one. So I think these two steps also help on this tracking of conditional meaningful human control in this sense. Do you agree with that, Markus?
Yes, I agree with this. Actually, well, another side effect, which is, I think, related a little bit, is we also tested what happens if the experts in the first step, they give very reasonable demonstrations, and then the expert in the second step tries to come up with completely malicious behavior, such that, for example, the expert prefers trajectories where vases are broken. And then we actually show that this is not possible, because if we assume, and you can actually prove some sort of guarantee, if all the reward functions, the marginal ones in the first step, behave reasonably well, and if the learning goes right, then in the second step we cannot provide malicious preferences. So this is just a more nice side effect of a two-step behavior. Yeah.
Thanks, Markus. Yeah, Cataline, you have a question. Go ahead.
Yeah, thank you. Thanks, Markus, for a very interesting presentation. I found it fascinating. I'd like to learn more about this combination of reinforcement learning and active learning. In particular, in this case, given the norms and so on, I was wondering, did you see maybe with expert opinion coming in that it made experts think, in the sense that I'm looking for, say, the hybrid intelligence point of view, where we say, you know, human and artificial intelligence together brings us further. So you show how it brings the AI further, but I would also like to see to what extent it could make humans think and say, well, actually, I want to change my norm maybe, or my strategy. Did you see any indications of that, or do you see the potential for that?
Well, indications, no, but I do see potential for sure. So actually, there's one sort of motivation for this research, which is that, I mean, the strength of reinforcement learning at its core is really to search through vast spaces of future possibilities. So the idea originally was that maybe, of course, people always have their preferences and they should be respected at all costs, but maybe we also think in short-sighted sometimes, and maybe the agent can come up in a way to save people and deliver packages and clean up things at the same time, right? And then maybe this possibility might change some humans' behavior. So you could incorporate maybe a feedback loop to the expert, where the expert then rethinks their preferences because they didn't even know it was possible to do certain things in combination. So I think that's the
yeah,
I think that's the promise, yeah.
Okay, cool. Well, if you continue in that kind of direction, I would be really interested to know about it and see if we can do something together.
All right, yeah. Yeah, it's very interesting.
Yeah, great, thanks. Yeah, do you have any other questions? Yeah, just remember, if you want to be on the video, you can also just type your question in the chat.
Yeah, maybe I have a question. So which relates, I think, to David's question about the relevance of this for the general kind of considerations of meaningful human control. And then I do agree that the kind of the value of understanding values is the major one. But I'm also wondering if there are any like implications for the tracing condition, which is basically I think it does become tricky, right? When you do have an agent that is trained by multiple humans, well trained or instructed or whatever, and then the agent does something which is not exactly what humans want, or there is an kind of some kind of consequences, but then it does become tricky to say, okay, which human of those experts would be the one to be responsible for that, right? So could you comment on that maybe?
Yes, I mean, I feel like this also relates a little bit to the last question. I think there's sort of a trade-off we sometimes make with these systems, because of course we would like the agent to come up with to not only imitate a single expert, because we want to leverage the power of artificial intelligence and learning from a lot of data, and I guess this in this AlphaGo system we had this move 37, which I guess only very few experts had ever played before, and it was just very very cool to learn from that. I guess here the problem is that if we want to leave open the possibility of coming up with new behaviors, then the more we leave open the possibility, the harder it will get for us to trace back who actually was responsible for this. And I think this might just really require more understanding of neural networks. There was actually, I think, quite recently, last week, a new paper about how reinforcement learning agents come up with new strategies, I think, in AlphaGo. So maybe that is a reasonable way of tackling that problem. But yeah, introducing more experts and more deep learning will not make it easy. That's all I can say, I think.
No, that's a very good answer, I think. Good, thanks.
Thanks. More questions? Yeah, I do have one question to Markus. So, Markus, so do you see as a possible extension of your framework towards like the unknowns? So let's say like this, because now you have like the criteria, like you have the cleaning or helping someone or delivering a package and the vases, right? So maybe there was something that it was not represented in the grid world. So for the or maybe in the real world, as of course that happens more often, because maybe there's something else besides like another goal, or instead of helping someone, I mean, I don't know, you have to, if you start, you have to protect, the robot has to protect from the rain or anything like this. So do you see this as an interesting step? So how to extend this in the framework you propose?
That's very difficult. I see. I mean, this reminds me a little bit of this inverse reinforcement learning, inverse reward design, sorry, paper, where of course the whole goal is to literally come up with a reward function that that is sort of robust to having forgotten some certain things and just being very risk sensitive. So I could see something like this being combined with this moral framework, where we say that this combination of reward functions, we don't treat it literally. We just treat it as some sort of soft prior information that if we come across some person that needs help, we should probably help it. But also if there's something unknown, we should probably avoid it, or some risk sensitive algorithm incorporate this in there. So just treat the reward function more as a suggestion than as a like literal rule for behavior. I feel like this is a little bit yeah, it's really difficult, but I think by learning distributions over reward functions, which is what we essentially do with this P of W, there is the possibility to explore the direction, because we have an uncertainty estimate of what the agent thinks is right and what is not. So we can use this uncertainty to, well, be less strict and keep the possibility open for unknowns.
Yeah. Okay. Yeah. Nice. I think nice that you mentioned also the inverse reward design. This paper is also, I think it fits very well, maybe on the first step, but also some adjusted ideas to the second step, to the preference giving. That could also be interesting. So thanks a lot. Yeah. Do we have any final questions? Someone else would like to ask something? Comment? Yeah, I think. So if you, Markus, you want me also to share the slides, right? You mentioned about the link there, so we can.
Sure, I can send you over the slides.
Yeah, we can make it available also on our website. So, so thanks a lot, Markus. It was really nice and great discussion. Thanks everyone for joining us today, and so yeah, see you at the following AiTech Agora. So.
All right, yeah, it was a pleasure talking to you all, and thanks for the great questions.
Thanks. Have a great day, everyone.
Bye.